Okay, so suppose we wanted to calculate the integral from 0 to 4 of the square root of x dx. So if I want to visualize what this means, the x values are running from 0 to 4. The function is the square root of x. And so that's equivalent to trying to figure the area under the curve y equals square root x. If we proceed as we did in class with the parabola problem, then we would try a regular partition where the delta x, k, is the same all the time. It's b minus a over n, which in this case would be, well, the entire interval is 4 units long, and so we would get 4 over n. If we did a right sum, then we would be evaluating the function at f of xk, where xk is the right endpoint, which would be 4k over n. And so the f of xk would be the square root of xk, which would be the square root of 4k over n. Oops. Which would be 2 over root n times the square root of k. All right, and so that would give us problems because we don't have any summation formulas for that. So instead of doing a regular partition, we're going to do a partition that isn't regular. We're going to have different lengths of the intervals. And so we're going to let x sub k be perfect squares, 4k squared over n squared, where k equals 1 up to n. So we're using perfect squares here, and the key idea is we need to get the rectangles to get skinnier and skinnier as n goes to infinity. So at some point when we figure out the delta xk, we have to make sure that goes to 0 as n goes to infinity. And not just any, the biggest. We need the largest of the delta xk's to go to 0. So let's look at what this partition is. Let's just look at the interval 0 to 4. Xk is 4k squared over n squared. So let's let n be 4, for instance. So I'd be wanting to chop this interval up into 4 pieces. So xk then would be 4k squared over n squared. So it would be k squared over 4. And so when k equals 0, I get x sub 0, as you would expect, is 0. When k equals 1, I get x sub 1 as a quarter. When k equals 2, I get x sub 2 is, 1 squared over 4, I should say, which is a quarter. I get 2 squared over 4, which is 1. When k is 3, I get 3 squared over 4, which is 9/4, which is 2.25. And then k4 is 4 squared over 4, which is 16 over 4, which is 4. All right? So I got 0. I'm going to try to do this as best I can. That would be 2. That would be 1. That would be 3. So instead of chopping it up into 4 equal pieces, like we've done before in a regular partition, we've got 0, and then we've got a quarter, and then we've got 1, and then 2 1/4, and then 4. All right, so these would be our, this would be our partition. So you can see we've got varying delta x k's. Right? So delta x1, the length of the first subinterval, would be a quarter minus 0. So delta x1 is a quarter. delta x2 would be 1 minus a quarter, which would be 3/4. Delta x3 would be 2.25 minus 1, that's 1.25. And finally, delta x4 is 4 minus 2.25, so that's 1.75. Right? So this is not a regular partition. They're not chopped up into equal pieces. So this will be convenient for us when we take f of xk, but then the delta xk is going to be a little messy. So our right endpoint sum is going to be the sum from k equals 1 to n of f of xk delta xk. We're still going to use the right endpoint, but the x sub k's are going to be rigged to make the function happy, but we'll just have to deal with that. So the f of xk in this case is the square root of xk. And if I take the square root of 4k squared over n squared, that's 2k over n. So that's nice. But the delta xk, well, that's going to be trickier because it's going to depend on the k. So what is delta xk? Well, that's xk minus x sub k minus 1. And so x sub k is 4k squared over n squared. X sub k minus 1 is the same thing, except instead of k, I've got k minus 1. So I'm going to factor out the 4 over n squared, and I'm going to be left with k squared minus k minus 1 squared. And now I need to go through and do the algebra on that. So I've got a k squared minus, and now I square this out. And then I'm going to subtract. So when I subtract this through, what do I get? I get a k squared minus k squared plus 2k minus 1. So I end up getting a 2k minus 1. Now, as n goes to infinity, right? If I look at the largest of these subintervals is going to be when k equals n. I still get a 4n over n. So I'll make the little note here. The largest delta xk is the last one, delta xn, which would be 4 over n times, 4 over n squared times 2n minus 1. And that does go to 0 as n goes to infinity, because the power in the numerator is only n, the power in the denominator is only n squared. So you can multiply that through and see that that does go to 0. So even though the rectangles aren't the same width, the largest width is going to 0. So let's go ahead and plug all this into our right endpoint sum. So that's the sum k goes from 1 to n. F of xk is how tall the rectangles are. Delta xk is how wide they are. The f of xk is 2k over n. The delta xk is 4 over n squared times 2k minus 1. And as before, we factor everything out that it doesn't depend on k, because k is what the counter is here. So I have a 2 times a 4, that's an 8 over n cubed times the summation k goes from 1 to n of k times 2k minus 1, which is 8 over n cubed summation k goes from 1 to n of 2k squared minus k. So I want to get this in terms of n using the formula sheet, and I'll take the limit as n goes to infinity. I'm just going to recopy that there. So using properties of sums, I'm going to break this up. That's basically just the the associative and commutative properties of finite subs. So I'm going to, finite sums rather, not finite subs. So I'm going to have this k go from 1 to n of 2k squared minus 8 over n cubed. Sum k go from 1 to n of k. Distributive property says I can pull that out to get a 16 over n cubed. Sum k goes from 1 to n, k squared minus 8 over n cubed. Sum k goes from 1 to n of k. So I get a 16 over n cubed, and this is where I use that formula sheet. So I'm going to look here at the formula sheet. Once again, I don't expect you to memorize these formulas. Whoops, I don't have it handy. I'm going to go find it. I apologize for that. All right, so here are the formulas. The sum of k is n times n plus 1 over 2. K squared is n times n plus 1 times 2n plus 1 all over 6. So this is n times n plus 1 times 2n plus 1 all over 6 minus 8 over n cubed, n times n plus 1 over 2. And so now I want to simplify this. So I've got a 16 over 6. So let's simplify that. That'll be left with the 3. That'll be left with an 8. So I have an 8 thirds. And I've got an n times n plus 1 times 2n plus 1 over n cubed. And then here I can cancel that and get a 4. N times n plus 1 over n cubed. All right, so this is my formula for RSN. So for example, if n equals 4, I would plug 4 into this, and that would give me the approximation using this partition, this particular partition here. All right, and I encourage you to go back and check what that is. All right, so I'm going to take the limit as n goes to infinity of RSN, which is the limit as n goes to infinity of this. All right, and because of what we know from chapter 2, it's the highest powers that are going to matter. So in the numerator here, the highest power of n, when you multiply that out, is going to be n times 2n. So you're going to get a 2n cubed plus some lower order terms. And as n goes to infinity, right, you're going to have that, basically that ratio of 2 times 8 thirds is 16 thirds. Over here, you're just going to get an n squared. And an n squared over an n is going to leave you with an n in the denominator, which means that's just going to go to 0. And so our final answer here is 16 thirds. Now we can check to see if this formula, this is the fundamental theorem of calculus, we talked about, we sort of mentioned it, we have an intuition that this should work. So let's look at the integral from 0 to 4 of root x dx. That'd be the integral from 0 to 4 of x to the 1/2 dx. So what's the integral of x to the 1/2? So you add 1, so that would be x to the 3/2, and divide by 3/2, which is multiplying by 2 thirds. And so the question is, well, let's see, we know what this is equal to. I plug in the 2 thirds times the 4 to the 3/2 minus the 2 thirds times the 0 to the 3/2. The square root of 4 is 2. 2 cubed is 8. So I get 16 thirds here. 0 to any positive power is 0. And sure enough, we get 16/3. Okay, so this seems to work. And we're going to prove the fundamental theorem of calculus next week. So we'll know that it works all the time. So this is not just a coincidence. All right, so here's an example of a right endpoint sum. We don't have a regular partition. In general, if we have a partition, say delta, x naught, x1 up to xn, the norm of delta is written this way. So this is the norm of delta. This is the maximum of all the delta xk's. All right. And so what we want is we want the maximum of those xk's to go to 0 to make sure the rectangles get skinnier. All right, so even if you don't chop it up into equal pieces, what you want is you want all of the rectangles to get skinnier and skinnier and skinnier. All right, so that'll do it for this supplemental video.